Welcome back. In this lecture, I will go through the introduction of statistical mechanics. So, the statistical mechanics are basically used for various different purposes. From the point of view of prediction of the property, the statistical mechanics is used pertaining to the modeling and the prediction of the properties of materials from the structure of the atoms and molecules which comprise the material. So, what we are interested in basically making use of the StatMech to generate the probability distribution of the energies of the atoms and molecules. And these averages over this distribution or the probability distributions are what experiments measure. Okay, this is something which is the core of the StatMech usage in predicting materials. So, let us first look at an example of the type of problem we wish to solve, and then we will introduce the basic concept of StatMech. Okay. So, let us consider this two-dimensional model of a 4-bead polymer change. Okay. So, this is a 4-bead polymer change of different conformation. So, we can categorize this conformation in two types. One is open conformation, which is basically the first excited macrostate, and the second is a closed conformation, which is a ground state. So, the close and this is open. Okay. And then what is our goal is to compute the probability distribution of the 4-bit chain occupying these two conformation, that is the fraction of the molecules that are in each conformation. Okay. So, we will come to in details of what is macrostate and macrostate and so forth in next few slides. So, let me just first go through the basic definition of various different terminology which we use in statistical mechanics. So, we will start with the energy levels. Okay. So, in this we will assume that each system, this is a molecular system or atomic system, has a well defined set of energy levels that the system can occupy. Okay. And the ground state will be the state having the lowest energy. States of high energy will be called excited states. We often use terminology such as macrostate and macrostate. So, what are macrostates? A macrostate is a snapshot of the system. Okay. When you measure system property, you measure averages over multiple macrostate. So, if we talk about a phase space, which basically is a combination of various different positions and the momentum. Okay. So, each point represent in a phase space some unique position and momentum of the particles. So, when you freeze them for a moment, then you basically generate a configuration, okay, or the snapshot of the system. So, in general the system may move like this, okay, and you are taking an average over this. So, you are taking you are measuring the system property over averages of this multiple macrostate, and thus you obtain a property in the measurement, and that is what typically the experiments outcomes are. So, we make use of the macrostate, but by collection of macrostates property we obtain a single properties. For example, it could be an average of energy, it could be an average of density, depending on what is the state variable. Okay. Now, in addition to microstate, we also make use of terminology called macrostate. Macrostate is defined by one or more thermodynamic property of the system, that is total energy or number of particle n. That means, when you are fixing thermodynamic property E, N, V, this would lead to a macrostate. Okay. A macrostate can have many different macrostates. The relation between macrostate and microstate is that of 1 to many. Okay. That means, for given macrostate, that is for given let us say total energy fixed, number of particle n fixed, there are in general numerous macrostate that satisfy the macrostate conditions. That means, there could be many macrostate having a total energy E, number of particle n, and a constant volume, for example. bit more complex system we can consider. The system we typically analyze can be more complex than the 4-bit polymer chain models. So, in realistic system the polymer chains could be many bits, but this is a very simple model. For our illustration, in general the energy of a system is given by intramolecular energies of the molecules, which includes translation, rotation, vibration, etc., and the intermolecular interaction between molecules, such as 2-body or 3-body or higher body interaction between molecules. So, if you consider many different snapshots of a system such as this which is shown here, okay, there could be many energy levels E1 to E2 and Ej depending on the arrangement of the particles. So, now in our nomenclature Ej represents the energy of one particular conformation of system, no matter how complex it is. Okay. And if we collect this various different properties, then the average of this energy level would be given as some weighted average over this individual energy levels to obtain average energy. And the question is basically what is Wi, that is weight of individual energy. This is something which we are going to learn very quickly. Let us consider how to derive this Wi, okay, the weight. So, let us consider a system having n particle of single type. So, that means they are of same type, okay, of so there is no mixture of system, this is of same type. And what we are considering in this that the system containing n particle has t different microstate with energy levels varying from E1 to Et in this form. Okay. Now, these energy levels are defined by the physics of the system, okay, and the problem that you want to solve. At this point, we will accept that the energy level exists, and we do not concern ourselves with how to compute the energy level of a system. In general, information about the energy level is deduced from quantum mechanics or from a macroscopic model. Okay. So, quantum mechanics means you are doing a very detailed solving Schrodinger equations to solve energy levels, or if they say a simple model could be Hartz-Fock and other models which we can which will have get a feeling on the later part of this course. So, what is our objective? Okay, our objective, as I said, we can our objective is basically to compute the probability of a given state that the system has, or that means the probability that the system in each microstate j. So, once we have P j, we should be able to calculate many different properties. So, in order to appreciate this, what we are going to do is we will work at a constant TVN. Okay, this is a macroscopic parameter, and for TVN or NVT, we know that at equilibrium the Helmholtz free energy would be minimum. Okay. That means dF is equal to du minus TdS should be 0 at minimum. Okay. Now, we have already discussed this, how to find out the maximum probability or the probability at equilibrium within the constraints. So, we have earlier in the lecture we have derived the maximization of the entropy with certain constraints. We will be trying to use this Lagrangian multiplier concept in this lecture as well. So, what is the entropy? We have already known this, we have already done this exercise earlier. So, we can make use of this expression of entropy in the differential form, which is this. Okay. What we are going to postulate for u, because we have to get this expression. So, ds of course, we can calculate from the probability. What about du? We can consider du to be d of average energy E, which will be average of all microscopic energies, minus T d s. Okay. So, this is what we are going to do here. ds of course, in terms of dp we have written here, and u is now an average of E, we can write as summation the probability of each macro state multiplied by E j. Okay. So, j is equal to 1 to t. T has a number of microstate, but that is what we said earlier, that the system has T different microstate with different energy levels. Now, having said that, now you can take the derivative of u, which will be in this case. Now, there is one important thing is that we have E j d p. So, p is a variable with respect to j's, but what about d e? Okay. Now, is energy level variable? Like the macroscopic energy u, the microscopic energy E j depends only on V and n. So, E is basically a function of V and n. Unlike u, the energy level E do not depend on the entropy or temperature. Okay. So, E actually depends only on the system. Okay. That comes directly from the quantum mechanics. It says that, well, for a given system you have a fixed energy levels, and what varies with temperature is basically the population of this energy level, not the energy level itself. So, the energy level do not depend on the temperature, but the population of the energy level depends on the temperature. So, with this we can simply say that at a constant V n, this is going to be 0. In other word, we can write d average differential value of the average energy is simply E d p. Okay. So, that means this part goes to 0. Now, given this and d s, we can now replace this in the final expression, okay, which is so you have this expression and this expression, this you can plug in df. Okay. Now, this is to minimize, that means this is basically the function which we are trying to minimize. We also need to understand that we have a constraint. Constraint is of course this is done, this is something which we have done it earlier also. Now, we have to minimize this function subject to the constraint here. So, we are going to put alpha times dp equal to 0. So, here we have introduced the Lagrangian multiplier alpha, and if you want to minimize f, we are going to now plug in this expression df is equal to du d of average E, which is this, comes here multiplied by dp and minus t ds, which is this, plus this alpha times dp here. Okay. And this is the function which we have to minimize, which using the Lagrangian multiplier, and this within the bracket, this must be 0. Based on that, we can calculate this expression. From here we get an expression for Pj. Star indicates that this is the probability corresponding to the minimum value of f. Okay. Now, in order to get rid of alpha, we make use of the fact that we can divide this as by we normalize it by summation Pj, which should be 1, and this is what we have done here. Okay. So, this we can get rid of this because alpha is a constant. So, what remains is a function this, which is e to power minus E j divided by k t and divided by summation of e to power minus E j by k t, and this we have done. We have said that summation of this factor, Boltzmann factor, is nothing but partition function q. Okay, and this expression which is relates to the Boltzmann factor of corresponding to the energy level of j divided by the partition function is called Boltzmann distribution function, or sometimes, or this is also called Boltzmann distribution law. Okay. So, this is the derivation based on the earlier exercises which we have done. Now, we are going to make use of it to understand a few things. Okay. This is something which we have already defined, that q is a partition function, which is simply sum of the Boltzmann factor corresponding to different energy levels. So, one can make use of this expression to understand relative population of two microstates. Let us assume that this is we are concerned of microstate I and j, and if we divide pi star divided by pi j, this is going to be e to the power minus E I minus E j divided by k t. This comes directly from the fact that we can write this as minus E I by k t divided by q, E minus E j divided by k t divided by q, q gets cancelled, and then you can rearrange to get this expression. Now, what this expression tells you? This expression tells you that more particle will have low energies and fewer particles will have higher energies. Okay. Now, because P I by P j, if it is greater than 1, it indicates that E I is less than E j. Okay. So, that is what it would tell you, because it means basically E j is at higher level and E I is at a lower level. Okay. So, but why is that? Why this is the case? Because if you can redo this exercise of arrangement as we have done earlier, this will allow more number of arrangement of the system in this way. Okay. Now, using this Maxwell distribution, we can also calculate the probability distribution of the velocities, or the distribution of the velocity. This is sometimes called Maxwell-Boltzmann distribution. So, according to the kinetic energy theory, gases and liquid can be regarded as Newtonian particles having mass m, velocity v, and kinetic energy epsilon, where the kinetic energy is given in this form. Okay. So, if you would like to calculate the distribution of velocity at temperature T, this is the distribution. This follows the Maxwell distribution model, and using this we can make use of various different things. For example, this can be connected to the temperature, okay, and you can try to solve various different aspects using these expressions here. Okay. So, we can find out the probability PV also. Based on this, you can make use of the energy levels to find out the velocity, the probability velocities also, okay, using simple the Maxwell distributions here. So, I am not going into details here, just wanted to tell you about the origin or the relations with the Maxwell-Boltzmann distribution, where these expressions are commonly used to connect with the temperature. Okay. So, let me come back again to the partition function. So, what does a partition function tells you? So, partition function provides a connection between a macroscopic thermodynamic property and a microscopic models. It is a sum of Boltzmann factor that specify how particles are partitioned throughout the accessible states. Okay. So, let us assume that the ground state is 0. In that case, the partition function can be written in this form, and assuming T energy levels. So, it will be 1 plus e to the power minus E 2 by k T and so forth until e to the power minus E t by k T. So, the partition function accounts for the number of states that are effectively accessible to a system at a given temperature. So, there is T levels, energy levels, but if we consider the energy levels, energies of different levels with respect to the ground energy, it tells you that that this is basically the sum of possible effective accessibility. So, this 1 plus the Boltzmann factor to access energy level 2, Boltzmann factor to access energy level 3, and so forth. Okay. So, it is simply the particles, the probability of how they are partitioned throughout the accessible state, that is what it tells you. And now, this is certainly dependent on the temperature. So, if you vary the temperature, T goes to 0 or T goes to infinity, you can clearly see what would be the partition function of such a limiting case, okay, which we can now understand. So, if you considering the high temperature, of course, all of them is going to be the Boltzmann factor e to the power j by k T, this factor is going to be 0, which essentially means e to the power which means basically e to the power minus E j by k T goes to 1, and in that case q goes to T, because q is going to be sum of this factor, okay, and this is going to be T, and in that case the probability for accessing a state j will be simply 1 by T. So, that means all the states will be equally populated, as that is what the idea is, okay, from here. If you consider low temperature, then e to the power j k T is going to be is approaches towards infinity. In that case, all the particles will occupy only the ground level as shown in this case. Probability of 1, the ground state will be 1, and the probability of all other state other than the ground state will be 0. Okay, in that case Q is going to be just 1. That is what it is here. Okay, there will be only one possible level, accessible level. So essentially it tells you that temperature is the only driving force by which you can populate the energy levels. Okay, and the Q represent basically the effective number of the levels which are getting accessible. Okay, let me further extend this exercise, and now let me define density of state. In macroscopic system, the number of microstates are very large. Therefore, many times it's easy to work with a microstate instead of microstate. Okay. So, the density of state is basically the number of microstate in a given microstate. So, if W, the density of state, is greater than 1, we call it, the energy levels are called degenerate. So, let us assume that the system has energy level from 1 to L max. Then the partition function, where we wrote simply Q is equal to summation here, where I is equal to all possible states. Now, you can rewrite this expression in terms of sum of energy levels, where W is basically the number of degenerate states corresponding to energy levels. Now, in that case, the probability of the system in energy level L. Now, we are not talking about energy system in a specific microstate. Here we are saying that the probability that a given system is energy level L is going to be written like this: P L is W of E L multiplied by energy, the Boltzmann factor of that particular energy level, divided by Q. Okay, this would be the probability of accessing a system is basically in a certain energy level L. Okay. Now, in general, you can choose both ways. You can use it in terms of macrostate or in terms of macrostate. So, that is pretty much up to you what to decide. So, let me just try to explain this understanding and try to solve a simple example, which is a 4-bit polymer chain, which we started with this lecture as an objective to solve. Here you have two possible energy states, or two possible states here. One is basically open state and the other one is a closed. In case of a closed case, you have one conformation. In case of open system or open macrostate, we have 4 possible conformation having the same energy epsilon 0, and other one we are considering to be 0 as a ground state. Now, what is we have to find is basically we have to find the probabilities here. So, we can consider first the partition function. So, what is the partition function? So, partition function is basically sum of all possible energy levels in terms of either I can write it in this way, energy levels and e to the power minus E L by k T, or I can write over all microstate. Okay. So, so here if I use it here, so it is going to be e to the power minus epsilon 0 by k T, because there are 4 of them, it becomes 4 plus e to the power minus 0 by k T for the case of ground 0. So, that means we have Q is 1 plus 4 e to the power minus epsilon 0 by k T. So, you can use it either this way or you can use either in this way, both will yield the same expression. Okay. Now, if the next question would be that what is the probability of the system is basically in a compact state, that will be e to the power minus 0 by k T divided by Q or 1 by Q. What about for the open system? This will be 4 e to the power minus epsilon by k T divided by Q. Now, you can use this and actually plot, because you have the handle or you have the expression Q in terms of T's. So, you can plot it also, and this is the expression which will come out, where it will clearly show you that the compact state preferred at low temperature, where the probability increases closer to 1, and open state is preferred at a very high temperature, okay, where the probability increases and the probability of compact state decreases at high temperature. You can continue this exercise also for 6-bed polymer chains, which I will leave you for you to try at your home. Okay, so this is a very simple introduction of statistical mechanics. We will see you in the next lecture.